A paddle wheel is fixed to the shaft of an engine. So you can see the engine here. So this is the engine. And this is the paddle wheel in blue color. And you have the shaft. This is the shaft. And the paddle wheel fixed to the shaft is revolving inside a closed hollow vessel containing water. So this is the vessel, and we have water inside the vessel. And this closed vessel is freely connected on the shaft. So the shaft can rotate and the vessel can also rotate freely. So they are not connected to each other rigidly. And to prevent the vessel from rotating, there is a restraint added in the form of a mass attached to its side to prevent the cylinder from rotating. So this mass applied is 60 kilograms. So the mass applied is 60 kilograms. The engine RPM is 650. The load is applied at a leverage of 1.2 meter and the quantity of water is 200 kilogram and the duration of the test is 20 minutes. So if we take a cross section of the whole setup, so it is going to look like this. So as we can see, this is the vessel. So this is the shaft. And this is the weight 60 kg. And the weight is connected at a leverage of 1.2 meter. So as we can see here, so the paddle wheel can rotate separately and the vessel can rotate separately from each other. And to prevent the vessel from rotating, so we have attached a mass of 60 kg. As the paddle wheel rotates, it agitates the water inside the vessel. And this movement of water creates resistance, which results in energy dissipation in the form of heat. So because of that, there is a heat generation. This heat is going to increase the temperature of the water. And as we can see, the 60 kg mass that is attached at a leverage of 1.2 meter creates a balancing torque to prevent the excessive movement caused by the shaft. So the amount of force required to hold the vessel steady is directly related to the engine's power. So we are supposed to find temperature rise for the given observations. Let's find the heat generated by the paddle shaft that is agitating the water inside the closed vessel. So we can start by writing the given in the question. So we have the engine's RPM. N is equal to 650 RPM. Then we have the weight of the load. Weight of the load is 60 kg. Leverage L is equal to 1.2 meter. The time of the test is equal to 20 minutes. And we have to find the temperature rise that was caused by the agitation of the water. To solve this problem, we need to use the sensible heating equation, which is Q is equal to mCp delta T, which is mass into specific heat capacity into the change in temperature or rise in temperature here, which we need to find. As the water gets agitated, the cylinder can freely move and the restraint 60 kilogram is going to prevent that from happening. the braking work done by the 60 kg mass is going to be equal to the agitation of the water, which directly generates the heat. So we can write it as the braking work done is going to be equal to the heat generated. So the work done here is going to be equal to 2 pi times RPM into the torque. To find the torque, the following expression, torque is equal to the force due to the mass 60 kg, that is the weight in Newton, times the leverage can be used. And since the weight or the mass is given here in 60 kilogram, we need to convert this into Newton. So as we know, 1 kilogram is equal to 10 Newton. So we can substitute the values given with the unit conversion, that is 60 kg, 10 Newton by 1 kg times 1.2 meter. So the torque is 720 Newton meter. So as the kilogram and the kilogram cancels out, we have Newton meter. To find the work done, we can substitute the torque in the expression 2 pi nt. So it's going to be 2 pi into 650 into 720. So we are going to find the work done for 20 minutes. So we are going to multiply the work done with the time 20 minutes. So finally we can get 58810,614.48 joule. So this is the work done. To find the heat gained, so we can use the expression. So to find the heat gained, in 20 minutes, we can use the expression Q is equal to M Cp of water delta T. Since we know the heat, so we can write the heat 58810,614.48 is equal to 200 kilogram into the specific heat capacity of water, which is 4.18 into 10 raised to 3 joule per kilogram Kelvin into the delta T. Let's write the units of all of these quantities. So joule, then we have kilogram, then we have joule per kilogram Kelvin. As we can see here, the kilogram and the kilogram cancels out, the joule and the joule cancels out, and finally we have unit of the temperature. So when we solve this, the rise in temperature is going to be 70.35 Kelvin. So now we have the rise in temperature, which is 70.35 Kelvin.